Everybody find their additional notes? What's that? You don't have those? They're with the permutations ones. Did you get the Okay, I got... Okay, so this reiterates the important idea that the order does not matter. So whenever you get to a permutation combination question, it is going to be the first thing that you think about. Does the order matter or not? And we've got our formula to actually take some white out here. Take that line out. Next year when you do IB, they use this N over R exclusively. However, in the grade 12 pre-calculus, we use NCR instead. And some special cases we can see with your cards here. Here's a deck of cards, 52 cards. How many ways can you choose all 52 of them? One way. There's a game called 52 Pickup. Has anyone ever not played that? Yeah, okay. And of course we've seen this. If you have 52 cards and you choose one of them, there'd be 52 ways. At the bottom here is the mathematical proof to show this idea, that 10 choose 6 is the same as 10 choose 4, which we've talked about already as well. All right, so here's our deck of cards. Some of you may or may not like to play poker. Now you can figure out all the possibilities of different poker hands and the possible poker hands in total that exist. So for example, I have 52 cards. A poker hand consists of 5 cards. Now when you get those 5 cards, you don't have to keep them in that same order. You can move them around. It doesn't matter which card you got first and which card you got last, so the order doesn't matter. And the total number of poker hands would just be 52 cards. We need to choose 5 of them. And this number I've seen fair enough, so I'm going to see if I've got it memorized. Every year I try to see if I can memorize it. How close did I get? 9. I think this one's 960. That's what I'm saying. How close am I? I might be off by a couple numbers. First 2 are right for sure. Is it right? Yeah. All right. So I do have it memorized. Another useless fact in my head. So there's almost 2.6 million different poker hands. So someone who likes to play poker, you could play for a very long time and never get the same hand. In fact, here we'll take out 5 cards right now. 1, 2, at random, 3, somewhat random since I can see these 2 cards. Mix them up again. 4, 5. Okay, be prepared to be amazed. We have the 9 of hearts, the 2 of spades, the ace of spades, the 4 of spades, and the jack of hearts. The chances of me getting these 5 cards was 1 in 2,598,960. You will probably never see these 5 cards picked ever again in your life. I'm just giving you guys a moment to absorb that. Of course, in poker, this would suck. If this was your final hand, you've got 1 card, high card ace. Yay. But nothing else in this is really, really good. Example 3, was this example 1? No, that was example 2. Oh, there's example 1. Okay, example 3. You've got a committee of 2 boys and 3 girls, and you need to select them from a class of 15 boys and 18 girls. Can you see that this is very similar to the store clerk question? We've got a committee. Committee's order doesn't matter. So we're thinking combinations. But there's two decisions that need to be made. We need to decide which boys are on there, and we need to decide which girls are on there. So we can make our space for our boys and a space for our girls. And there's 15 boys, and we need to choose 2 of them. And there's 18 girls, and we need to choose 3 of them. 35, 85, 680. Lots of different possible committees. So let's say you have a big class and you need to make them into 3 groups. Group A needs 8 people, Group B needs 5, and Group C needs 7. And the order doesn't matter in the groups. So we could think of this as combinations. If we choose Group A first, and it doesn't matter which group you choose first, and we'll see that in our factorial notation at the end. But if I choose, oh, there's more than 15 people. How many are there? 20? There's 20 people, and I want to choose Group A first. I need to choose 8 of them to be in Group A. That would be my first decision. Then my second decision is I have to pick Group B. How many people are left? 12 people are left, and I need to choose 7 of them to be in Group B. So this is Group A, this is Group B. And my third decision would be Group C. How many people are left? 5. And I need to choose all 5 of them.
But doesn't Group B need 5? I guess
Group, oh, Group B needs 5. Thank you. Here we go. Group B needs 5. Group C needs 7. There'd be 7 people left. Which makes sense. Once you've picked Group A and Group B, anybody who's left will be in Group C. Now, when we do the factorial, this would be 20 factorial over 8 factorial, 12 factorial. And this one would be 12 factorial over 5 factorial, 7 factorial. And this one's going to be 7 factorial over 7 factorial, 0 factorial. So in the formulas, we see why we need a 1 for 0 factorial. Otherwise, the formula wouldn't work. Now, if we do some simplifying here, can you see that these 7s would cancel out? In fact, that last one, 7, choose 7, should just be 1. Can you see that the 12 simplifies away? And all we're left with is 20 factorial over 8 factorial, 5 factorial, 7 factorial. And you've seen answers like this before. When have you done questions where the answers look like that? What kind of permutations? What kind of question in permutations? Flags that are the same color, like Mississippi with the same letters. Whenever there's identical objects with that repetition, you had to divide out. And another way that some people sometimes solve this same question is they think of it as identical objects. If you're in Group A, you're an A, so there's 8 A's. And then 5 B's, and then 7 C's, which would be 20 factorial over 8 factorial, 7 factorial, 5 factorial. Same thing. Exactly the same. But after time, combinations and choosing seems like an easier strategy than using a whole bunch of A's, B's, and C's. You will think of the combinations quicker because you're like, I need to choose somebody. I need to put them in a group, and the order doesn't matter. All right. Poker hands with no clubs. If I wanted to count all the poker hands without clubs, does it make sense if I take out every single club from my deck and then deal myself 5 cards, I would be guaranteed not to get any clubs, right? So now I've taken out the 13 clubs. I have 39 cards left. I need to choose 5 of them. And when I choose those 5, guaranteed, woohoo, I got no clubs. So sometimes we get a restriction in the question that's going to change the size that we have to choose from. And in this case, in order to guarantee that I have no clubs, I take 39, I choose 5 of them. That's a pretty looking number. 575757. Now, for part B here, I'm going to put on my salesman pitch. I'm going to give you 3 different ways to solve this question. All 3 might all be wrong. All 3 might all be right. 2 might be right and 1 might be wrong. Or 1 might be right and 2 are wrong. But I'm going to try and convince you that all 3 are right. And then you have to just tell me afterwards, after you've heard the arguments for each one, which one you think is right, or if none of them are right, or if all of them are right. Are you ready? Okay. Well, here's my deck of cards. I want to choose at least 1 club. Well, in order to guarantee that I have at least 1 club, I've got the 13 clubs out here right now. I'm going to choose 1 of them at random. 13, choose 1. That gets me 1 club. Now, I could get more than 1 club, but I don't need to have more than 1 club. So now if I put these 13 cards back in the deck, shuffle them up, and randomly pick 4 more cards, I now have 51 cards in the deck, and I'm going to choose 4 more. So I've chosen 5 cards, and I have at least 1 club. That's strategy number 1. Strategy number 2. Well, I'm going to break this up into cases, because at least 1 club could mean 1 club and 4 other cards, 2 clubs and 3 other cards, 3 clubs and 2 other clubs, 4 clubs and 1 other card, or all 5 clubs. So I've got my 13 clubs separated. Case 1, I'm going to call 1 club. So I choose 1 club, and then from the other 39 cards that are left, I'd have to choose 4 more. That would give me exactly 1 club. Case 2, I choose 2 clubs. 13 clubs, choose 2 of them, and then from the other 39 cards, choose 3 others. Case 3 is 3 clubs. 13, choose 3, times 39, choose 2. Case 4, I choose 4 clubs. 13, choose 4 of them. 39, choose 1 other card. And finally, the last case is I choose all 5 clubs, which would just be 13 clubs, choose 5 of them. If I take each of those cases and add them up, then I would have all the ways that I could get at least 1 club. Because I counted 1 club separate, 2 clubs separate, 3 clubs separate, 4 clubs separate, 5 clubs separate. That's my method number 2. Method number 3, I'm going to use what we did previously. Previously, we counted all the hands with no clubs, so I'm going to use the not strategy. And in the not strategy, that says count all of them and subtract the bad ones. Well, all the poker hands we already know is 52, choose 5. And the bad ones would be hands without any clubs. And we figured that out in part A, which was 39, choose 5. If I subtract all the hands with no clubs, then I'm going to be guaranteed to get all the rest having at least 1 club. So there are the 3 different ones. You have to decide now if you think that all 3 strategies are right, all 3 strategies are wrong, or which ones are right and which ones are wrong. And hopefully I was convincing on all of them. What do you think? You hate these? So now there are the actual answers that we figured out for each of them. And 2 of them are the same and 1 of them is different. So obviously not all 3 are right. Now arguments for whether you think the first one is right and the next 2 are wrong, or arguments to say that the next 2 are right and the first one is wrong. You're going to go with right, wrong, wrong, and you're going to go with wrong, right, right.
I just want the not strategy to be right. I don't want that to be right. I just want.
You want the not strategy to be right. So then you want the first one to be wrong. So you have to come up with a good reason why the first one's wrong, and you have to come up with a good reason why the second and third one are wrong. Just a feeling, just 'cause doesn't.
Because you can get 4 clubs from the 51 cards. You can get 3, or you can get 9.
Right.
That's the same as case.
Oh, case. So this and this are the same? The numbers are different. Yeah.
I just wanted to be right faster. You just tell us.
Can I just tell you? You don't like the game anymore? How many poker hands are there? That's a hint. Well, we figured it out. Turn back. It's a big number. 2 point how many million? 2.6 million, just a little bit less? Okay. So now let's look at the first one. If there's 2.6 million total poker hands, how can there be possibly more poker hands that have at least 1 club than the total number? This number here is more than total poker hands possible. So that can't be right because we have a restriction here that has at least 1 club, and we can't get more hands that are possible with a restriction that should be less. Now why does that first one give us a problem? Well, I'll show you why with an example. If I choose 13, choose 1. I pull out a card, there's my 4 of clubs. I chose in the 13, choose 1, the 4 of clubs. Then I put these ones back, mix them up, and I pick more cards. Let's say in the next 4 I pick the ace of hearts, the 5 of diamonds, the 7 of diamonds, and the 8 of clubs. That is a possibility, right? That's one possibility. Now what could have happened in my first try is I could have picked the 8 of clubs to begin with. Then, when I put the other cards in and shuffle them up, I could have gotten the 8 of hearts again, the 5 of diamonds again, the 7 of diamonds, and then the 4 of clubs. And according to this strategy, those would be counted differently. But those are the exact same hand. The problem with this strategy is you've made some overlap in your two counting procedures. And if you create an overlap in your two counting procedures, you're going to count some things twice without knowing it. So here I chose the 4 of clubs, and later I could choose the 8 of clubs, but I could have also chosen the 8 of clubs here and the 4 of clubs later, and that will account for many times counting too much. In fact, we counted over 1 million times too many. We had a bunch of repetitions built in. Whereas in the second one with the cases, do you see that in each case, there's no overlap? This is choosing just clubs, this is choosing not clubs. This is choosing just clubs, this is choosing not clubs. And so there's no overlap here. And yes, the best strategy for this one as far as work goes is to use the not strategy, because you would have all of them minus the bad ones, and what would be left are ones with at least one club. In fact, when you see a question with at least, often a not strategy or cases have to be employed. And you decide on which one based on which one's going to be less work. But both would work. The last thing we're going to do is a bunch of poker hands.